But no problem. So before we actually start the lecture, so let me just give you a overview what will happen next days, and particularly on Saturday. So, I mean, today it's big day. Afternoon, you better come out with results and models and so on. And tomorrow, you would have to use the time for preparing a presentation. But I know that at least part of the day will be consumed by new calculations, new models, and interpretation of what the results. Okay, that's normal. And so for the presentations, so practical things. There will be a time slot of 35 minutes for each group. You have 20 minutes presentation and 15 minutes question time. Okay? So you should prepare a 20 minutes presentation. This means that if you are going to use the projector, PowerPoint, PDF, whatever, the number of slides should not be like 60, 70. You will never do it in 20 minutes, okay? So you more or less try to be concise and so on. It would be the best case to have just one person giving the talk and presenting things in a unified way. I know sometimes this doesn't happen because people don't feel comfortable talking about another area. Persons are physicists, doesn't feel okay to give them more biological insights, and vice versa. People from biology are not comfortable with the equations. So you can have two, right? Two persons. But in principle, ideally, one. So, and try to prepare the talk. You may have some training before and so on. And have your presentation ready on Saturday. So this seems obvious, but yeah, but that sometimes the guys in group number 7 presentation is in the afternoon, and so okay, we have the morning to finish, and then you see people that don't pay attention to the presentation, still finishing the things and so on. So try to say, okay, we will do everything until Friday evening. Okay, so. Yeah, so that's the next point, yeah. The best thing is, you know, we will have computers. We have this old one, Windows, and otherwise if you have a problem with that, you can use mine. The best situation is to have PDFs. Because PDF goes anywhere without any special program. Every computer has Acrobat, so this is the best case. But, well, maybe you prefer to do it in PowerPoint, or I don't know if there's other preferred software. You can. I mean, there's PowerPoint on this computer here. But, you know, sometimes there are questions about compatibility of the versions of PowerPoint and of Microsoft things, blah, blah, blah. So better PDF, but okay, you are free to choose. But one thing that when you go to conferences and workshops around the world and so on, which is really embarrassing and it's kind of shame, is the person comes with their own computer and then it doesn't work. The projector is not compatible, whatever. So you have two options. First is use our computers and test them before. The second option is you may use one of your computers. But, I mean, if you are talking in the morning, you arrive before 10 o'clock, and you test if everything is going okay, if everything is working. Sometimes you have movies. Is the movie working? Is it okay? Use the projector, because it's different when you just test it in your computer. But when you test the computer connected to the projector, sometimes there are messy things happening and so on. So please be sure that when it's time for your presentation, you come and you start the presentation, I mean, right away. You will not get with all the problem with your computer and so on. Although I say this every year there's somebody who has a problem with the computer because, oh, I didn't think about it, okay? I didn't test, okay? So please, okay, that's the professional part of being a scientist. You are invited to give a seminar, you come with a prepared seminar which works on every computer, or your computer has been tested, and so on, so on, so on, okay? So. We don't want the story of what you did or what you tried, what was successful or not. We want a talk about your subject. You begin, that's my subject, okay? Our modeling approach is this one. We consider certain biological mechanisms. We model this through these equations. We solve the equations, we obtain results, and we go back to the biology and give you an interpretation of what our results mean biologically, what is the kind of advance that you could find, and if you have time, talk a little bit about future perspectives. Okay, so that's the usual thing, okay? We don't want to know that you have really spent 12 hours a day and the model didn't work, but at the end it worked, and so on. Okay, this you talk with your colleagues, with the monitors, with me, and so on. Presentation is, that's the topic and that's my contribution. Okay. So, we start at 10. Then we go from 10 to 12 with the first 3 presentations. Then we start again at 1:30. We have 1 hour and 30 minutes for lunch. And we go up until 5:30, okay? 17:30, okay? We will end, if everything is on time, at 5:30, okay? So that's the perspective. If there is a group with people that have to leave because they have planes and so on, then talk to me. We can put you to talk in the morning or in the early afternoon, okay? So that's it. That will happen on Saturday, and so you should be aware. We are giving you 20 minutes. 20 minutes is a lot of time. If you go to workshops or conferences or whatever, and you are given 20 minutes, you are usually fine. That's good. Okay, that's okay. And we have 15 minutes for questions. 15 minutes for questions is nice. Why? Usually in conferences you don't get this? Okay, you get 20 minutes and total that amount of time. 15 plus 5. And then people usually talk 18, and then there's the situation that says, we have time for one question. Okay? That happens all the time, and that's really a mess. So we want that people can really discuss, because that's the moment people will see your results, and then that's the moment that you can discuss with the other people, okay? So, therefore, 20 minutes, it's a lot. Please stick to 20 minutes, because we want really 15 minutes, and you can be sure there will be 15 minutes of questions, because people ask a lot of questions, and that's really fine, okay? So let's start the lecture. So is there any question about the organization of our Saturday journey? Okay, so fine. So today we will talk about spatial population dynamics. So this, until now, we have only seen problems where we consider total populations, okay? So we have functions like the predator population, like the, where's the chalk? It's gone away. So you have functions like the predator population, the population of some species or whatever, are functions of time, okay? So they are usually just a function of time. So we don't talk about space. Okay? So, but it is a legitimate and interesting scientific problem to say how do the populations spread or distribute on space. Is everybody in just one part of this of a certain domain? Is it homogeneous? Is it heterogeneous? Is it time varying? Is it static? So many questions about distribution of on what happens on space. And space might be important for your problem. So one typical problem, there are two typical problems that you address with, I mean, it's too simplified, it's not two problems, but some standard problems is invasion, the dynamics of a biological invasion. So you have a resident population, and then there's invading population. So once say that the population that invades is able to actually invade, and you can see that how will this happen in space and time? Okay? Will you have a front of invasion? Will you have patches of invasion? You can have many things, depending also on the structure of your habitats. So that's one typical problem. The other typical problem is sometimes space is limited. It's all limited, actually, and but sometimes it's really limited to the point that it really affects the population dynamics. There are borders, there are barriers, there are things like that, different habitats. So, so a classical problem is also to say, how does the restriction on space, the fact that it is limited, affect your population levels? Okay? And this connects to more complex problems, like maybe your domain is really not homogeneous. So today we will talk about homogeneous problems, because we will look more like problems in like invasions. But so before we go for the mathematics, it's actually a very important problems in spatial ecology is that space is not homogeneous, right? So space, when I say space, this is not our physical, it's the same space that physicists or mathematicians talk about, okay? That's the actual space with the actual habitats, okay? And this is non-homogeneous. For instance, if you look to the Brazilian Atlantic forest, it's completely fragmented, okay? So there's a lot of fragments, and you could ask yourself, so what's the effect of being fragmented? What's the difference between non-fragmented and a fragmented habitat? These are questions that are still very, very much in heated debate about this, okay? This is spatial problems, and so there are many problems that are about heterogeneous space. And you can also have problems where space is so heterogeneous that it's just made out of patches of habitat with what people call a matrix, which is a region that can be sometimes crossed, but there's no resident population. And then when you have highly fragmented and distant patches, then you have other approaches, which is called metapopulation dynamics, and so on and so on. So today, we will look for the case of an homogeneous infinite space, in principle a two-dimensional infinite space. And we want to discuss the basic equations that will govern the population dynamics on this. So, So let's start. You would say, okay, but 5 minutes ago I told you that the population space is always limited, and now you start with an infinite space. Yeah, sometimes, yeah, I mean, sometimes the space is such that it's actually during a certain time scale there is no limitation because the borders are very far away. Okay? So then you can look at the problems as with the formalism of infinite space. So, okay. So we will look for what is called diffusion. So this is not working. What happens to my pointer? Okay, just a minute. Why don't you work? Yeah, I guess it's gone. Should work. Well, yeah, all those high-tech things are usually unpredictable. So, and we will discuss reaction diffusion equations. Okay, so that's just a buzz name. When you hear about reaction diffusion, it's things like we will discuss here. So, okay, this is just a slide with what I just told you here. And the first important thing is now, what is our basic variables? So up to now, the basic variable has been always a function of time, which is the total population in a certain part of space that you are considering. That it's always like this. So now, if you want to consider space and time, there's no such thing as total population. You want the population at a certain part of space, and so on. So, but then you don't want really the population at a certain point of space, because that's not very precise. So it would be better to have the density of individuals per unit of space. Okay? So we will work with densities, usually by some, I don't know, curious tradition. Density is people like to use rho for density. And this now is a function of time and of space. So, how many spatial variables do we need? Okay. So, for problems in ecology, usually it's 2. Space, if you look, you want to study the distribution of population, if you look for terrestrial dynamics and so on, it's usually 2-dimensional, okay? There's no, then you would say, no, but there are things like birds that there's a 3rd dimension. But usually this 3rd dimension is much smaller than the other 2 dimensions. And many species, if you say, no, I'm looking for fish, and fish is actually 3-dimensional, there's no no limitation. But it is also usual that species usually have a preferred depth. So it's stratified, actually. The ocean is stratified and by physical properties, which induce a stratification of population of fish or any marine animal. So in fact, using 2 dimensions is pretty okay. It's very, very rare that you need to use a 3rd dimension. So in principle, this should be 2-dimensional space. Okay? X and Y, the usual 2-dimensional notation. Therefore, your density is a function of 3 variables. Oh, come on, we had just 1 and we went directly for 3. Right? So, yeah, it turns out that when you work in homogeneous space, you can do the mathematics with 1-dimensional problems most of the time. And it's trivial to find the 2-dimensional analogy, because that's kind of symmetry. If it's homogeneous and isotropic, I mean, there's no preferred directions and so on. Okay, if it's homogeneous, the space, then everything that happens in X should more or less happen in Y, and usually the equation that you derive for dynamics of your density can be solved with only one spatial variable, and then it's obvious what will happen in 2 dimensions. That's what we will do here. So, now, we have studied until yesterday the principles of the dynamics of population dynamics of species. And now we need to introduce how species use a space. Therefore, we will need new principles. So this is a vast problem. It's an enormous problem. How do people, species, either animal or vegetal or whatever, use space? Okay? So, because they use space, and sometimes it is connected to foraging behavior, hunting, sometimes it is just looking for new space to be in a less densely populated region. So there are many things that are behavioral, that imply certain use of the space, and this is the whole area of spatial ecology. And we will have a school on spatial ecology next year after the first week. This year we have community ecology next week. Some of you are staying for that school. Next year we will have the same school in the first, in this week, and the next school will be about spatial ecology, with some focus on vegetation dynamics. But so, therefore, if there's this whole school, it means that this is an actual research area to see how you scale behavioral aspects of movement to actual spatial redistribution of the population. Okay? So spatial ecology is, I mean, this is not the only thing that is interesting, because we should not make the confusion between spatial ecology and movement ecology, because there's a spatial ecology of species that don't move. For instance, trees. So you don't see the tree moving around, foraging, but on a larger time scale, you know that there is forests or whatever vegetation expands, retracts, and so on. There's a spatial redistribution of the population, even if the individual does not move. There is a way of using space, even by species that don't move. Okay, and movement ecology is the ecology of the movement. So you are restricting yourself to study how species move and how does impact this at the population level. Right? So the different things. Yeah. Oops. In this context, the habitat is the same everywhere. Okay. In this context, the homogeneous space is the habitat is, for instance, if you go to a large forest and it's more or less homogeneous, then obviously there are borders, but if you are looking on a spatial scale that is much less than the dimensions of the forest, then can be considered homogeneous. But the question is difficult to answer in a more profound way. I will show you examples where homogeneous space theory works well, and the space is actually super heterogeneous. So sometimes the heterogeneities in space do not affect sometimes the spatial movement or the spatial redistribution of the population. They just don't care. So you say, maybe I have a certain region here as a river. Okay, it's clearly heterogeneous. But I mean, if you're looking for, I don't know, birds, they don't care about the river. Okay, so there are, what is important is the interaction of your species with space, with the structure that makes up your habitat and so on. That's the important thing. And sometimes you can have, for instance, just to give you an example, an old work of mine with Renato Coutinho and Wesley from Piracicaba was about blowfly invasion in Brazil. There's a kind of African blowfly that invaded Brazil, coming from Angola, in the time of the civil war of Angola and so on, blah, blah, blah. And so we could study with data and with theory the spatial aspects of this invasion. And we used a model which is completely homogeneous. And obviously, and this is for the state of São Paulo. We had only data for the state of São Paulo. And then you look how the actual invasion took place. And to a large extent, everything worked with homogeneous space. Right? Even, there are cities, there are plantations, there are lots of things, rivers, mountains, and so on. But blowflies actually didn't see these things as barriers, and so they more or less spread homogeneously over the state of São Paulo. More or less, because if you are looking at the scale of the states of São Paulo, you are not caring about the movement on a daily basis of a blowfly, okay? Which would clearly have heterogeneous things. But if you look at a larger structure, then sometimes what is heterogeneous is well modeled by something which is homogeneous, okay? In mathematically, that's what you will see in the next moment. Yes, you will have partial differential equations, but the parameters are constants, okay? Or at least don't depend on space. And you see, if you want to go for heterogeneous space, there's an obvious way. Okay? So, we want to study the things at the level of a spatial scale much larger than the typical scale of the movement, of the daily movement of our species, okay? So to give you an example, let us see that we want to discuss the distribution of, or the invasion of ants in a certain region. So ants on a daily basis just go one after the other, okay? So that's the spatial dynamics at the scale of minutes, okay? Just go on a line, okay? But if you want to look for the invasions, you don't care what they do every day and every minute. So you want to look at the scale, say, of many, many, many kilometers, and you want to know where can I find this species of ants. It's not the movement, daily movement that's important. It's actually the creation, the expansion of where you can have these ants or not. Okay, so we will look at this larger time scale here today. Okay, so and we will assume that this situation is well modeled by a process called diffusion. And here, okay, this is sometimes people they say, oh, diffusion. Because what is diffusion? Diffusion at this point we will consider to be an analogy of particles moving in a Brownian motion, random movement, like with a distribution of steps following a Gaussian, and a random movement at the level of the individuals, okay? So one approach, which would be very nice, is to consider a stochastic dynamics of populations and write down the stochastic dynamics and then obtain averaged values to obtain a larger scale dynamics. That is standard. We won't do it here because this implies that I have to introduce all the formalism of stochastic dynamics, which would take the whole class to do. So, but you can find this, and there are textbooks on that and so on, and what I will be discussing here on a larger time scale, it's actually compatible with stochastic dynamics. Also, it's kind of mean field theory of stochastic dynamics. So we will use something which is called the Fick law. So what is this? The Fickian diffusion law states that the flux of material, okay, in this our case, material is just our species, is proportional to the gradient of the density of the material. So rho is the density, and I say the flux is proportional to the gradient. So okay, if you are not mathematically trained, the gradient is a vector of the partial derivatives of rho. So and if you don't understand what's a partial derivative, it's just you have a function of, say, two variables. You can x and t. You can take the derivative of the function with respect to t, considering that x is like a constant, or vice versa. Okay, so these are partial derivatives. Okay, so and we will consider that the spatial gradient here is given that the flux is proportional to minus some constant, which will be called diffusion constant, times the gradient. So what is the idea? So say you have a population distribution like that, okay? Population is concentrated in a certain region, okay? So take a point here. I'm looking for a one-dimensional case, therefore there's no y. If this is rho of x, okay, the gradient becomes only the partial derivative, d rho dx. Look at this point, okay? This means that d rho dx here, if you go here's x, yeah? If you go look at this, here d rho dx is actually negative. And I'm saying that the flux is minus d times d rho dx. Therefore, at this point, the flux is positive, which means that you are moving in this way. And the steeper, the faster. Okay? So diffusion is the tendency, macroscopically, it's the tendency to flatten out everything, to homogenize things. Okay? So this thing here, if the derivative at a certain point here is, for instance, it's smaller, then this flux here is smaller than here. So this will give you a tendency to, to spread out because of the minus sign, spread out, okay? So that's what we are assuming. And that's an analogy to the kinetic theory of gases. So gas dynamics can be studied with statistical mechanics, but even before statistical mechanics, there was something called the kinetic theory of gases. And this this kind of situation appears there, and that's what you would have if you're looking for the expansion of material expansion of a gas. Okay. Well, okay. So to simplify the mathematics, okay, to don't be around with this curious symbols. This symbol here just means that, okay? That's the vector of the derivatives of rho, okay? But, to make all things simpler, okay, let us just say that rho is proportional to, the space is one-dimensional, and therefore the gradient just becomes a partial derivative. It's just nicer, okay? And it's easier to understand. So actually, everything's the same in 2 dimensions. But for the benefit of people that have not done vector calculus, that's the name of the thing. If you have not studied vector calculus, it's better to be just with the partial derivative. Okay. So next, we will impose second hypothesis. So the first one is that the movement obeys, the density obeys Fick's law, okay? And now I will say that the movement does not create or kills the species. Therefore, movement is separated from the vital dynamics of the population. Dynamics is separated from movement. So you don't have the equations that describing the movement should not generate new individuals or should not kill individuals, because you want to separate movement from the dynamics of the population. Okay, that's a hypothesis. It works well for many cases. Maybe it doesn't work for all, but it's a good hypothesis. Hello? Therefore, I will impose that the law of called mass conservation, but in our case, this is the conservation of the number of individuals. Right? So individuals, due to movement, there is no creation of new individuals. We are just looking the spatial distribution of the population. We are not looking how the birth and saturation and predation and competition affect the population at this point. So we want only the spatial part. So the rate of change in time of the quantity of individuals in a given region of space is equal to the flux through the borders. Okay? So the only way to have given a certain part of space, the number of individuals there can change only through the flux, positive or negative flux, at the borders of this region. Okay? There's no birth or no death at that point. Okay? So you have a certain population. No. Because okay. It's a total derivative. Yeah. Okay. Because the integral is not dependent on x, actually. Okay. Yeah. Good. You're the first one that noticed this over the years. Okay. I use this equation every year. Nobody noticed that. Actually. So, say you have a part of space here, which need not be limited, but let's consider that you have a space infinite, but I look at a certain part of space and I have a distribution of population, of the density of the population here. So it's a function of time and of space. And I'm saying that this number of individuals here inside a certain given region can only vary through fluxes at the borders of the region. Okay? It can change in time here. Yeah, can change in time. But the total number of individuals, and the total number of individuals is what? Here you have the density, Okay, it's a function of space and time. If I say this is x0 and this is x1, then this is just the integral from x0 to x1. Okay? That's the number of individuals in a given region of space. And this thing can change in time only due to movement through the borders of this region, therefore through fluxes. Okay? That's the only way. So, therefore, what I want is to have that the number of individuals is this thing, just the same thing I just wrote there. And so the time derivative of this is equal to the difference of the fluxes at the borders. And the border is x0 and x1, okay? So that you see here why I prefer to use one-dimensional dynamics, because if you go for two-dimensional space, then you'd have something like that. You have a domain, a certain region, then the border, if the region is usually called omega, the border will be called delta omega, and I have to know how to calculate the flux to the border, which is a problem, and it's not a problem. Technically, it's in vector calculus, you see, but you need to define the normal and the flux and so on. Okay. You see, you're happy that I didn't go for the two-dimensional case at this point, because it would be unnecessarily complicated. Okay? So, therefore, that's the population, and it can only change due to the flux. And now, okay, if you really have never went through a more advanced calculus course, maybe you won't understand the next slide, but okay, you can come back later and everything will be fine. Okay, so now what you do need, you have, this is our law. This is, you can think this is an integral law, but you know, there are such things called as integral equations. We don't want them. We want to go back to our nice differential equations, which are the simplest object in the universe. So, so we will take the region very small. Therefore, I will say x1 here is just the x0 plus some delta. I use some delta x. And delta x is very small. Okay? You want to do this. We want to have a small region. And then obviously we'll take the limit of infinitesimal small region. So that's this. And if you do this, if you remember a little bit about your calculus course, calculus, I don't know, 102 maybe. So if x0, if x1 minus x0 is very small, when it goes to 0, okay, this thing here is just, and if you call this delta x, it's just the delta x times rho. Okay? So that's the first thing you have to notice, yeah, which is very nice, yeah, because you got rid of the integral, okay? No integral anymore. We don't like integrals here. So the second step is also now x, the flux at x1 can be calculated in terms of the flux at x0 when delta x goes to 0. That's called a Taylor expansion. And I don't want to show you a Taylor expansion. It's very easy, but I mean, it's so if you have never seen this, just believe me, okay? Just take I have faith in my professor. Okay? Give me credit. So this is you can calculate x at the flux at x1 being the flux at x0 plus some increment, which depends only on the time derivative of the flux at the point x0. Therefore, this equation here, I have now expression for the left-hand side, which is d rho dt times delta x. And I have an expression for the right-hand side, which comes from x0 minus x1 being exactly this. Okay? Now I use the Fick law. And I use the Fick law and I get the flux is proportional. And d is the proportionality constant to d rho dx. Therefore, I have already the derivative of the flux on space. And now the derivative itself, the flux itself is a derivative that gives you a second derivative here. And the equation you obtain is this one. There's a partial differential equation for the function rho, which is a function of x and t, such that the derivative in time of rho is proportional to the second derivative of rho in the spatial variable. Okay? So if you went to two dimensions in infinite space, you would obtain just that instead of the second derivative of rho with respect to x, you would have the same thing plus the second derivative with respect to y. So it's analogous in the next, and therefore there's kind of symmetry between x and y. So now let us come to some facts that are important about partial differential equations. Okay, so what does it mean to solve a partial differential equation? Okay, first thing. So obviously we will say that the most basic thing is find the function that obeys the relation. Well, this is not well-posed mathematical problem. Actually, you have to with ordinary differential equations, you always have to, in order to have one solution, a unique solution, you need to give the initial conditions. Okay? All the time you have to say the initial condition. So you can ask, well, I probably have to give the initial conditions also here. But if you now take the time equal to 0, you get a function, and not you have to say, you have to give the initial distribution. So this is one problem that you can study. On infinite space, I give an initial distribution, but this is not enough. Because of reasons that are more technical, as you have a second spatial derivative, you need more than just the initial distribution. You have to give the behavior at the borders, for instance. If the space is infinite, the behavior at the borders means just the things like the function goes to 0 or goes to a constant on x going to minus or plus infinity. If you have a restricted space, you have to say what happens at the borders of your space. You could have borders which are like an aquarium. You have a border which is really a barrier. Then say we are here and I'm a member of the species and I'm moving here in a Brownian motion, and I come here and hit this, I go back. Okay, so this is a barrier, means that there's no flux there outside. No flux outside means that the derivative of the function with respect to the direction x is 0 at the border. So this is as a condition at the border. There could be the case where you have two different kinds of habitats, but there's no barrier at all, and your species are kind of dumb, and it just goes on. Okay? Then in this case, usually you have a flux, you have to give the behavior of the population at the border, means most of the time, say the population is 0 at the border, or a certain constant at the border, or something like that. Okay? So these are different mathematical problems which will give you different solutions. So partial differential equations, therefore, is more rich and more difficult than ordinary differential equations. That's why Renato in the second day on on Monday, giving the lecture at the evening. So partial differential equations is trivial for numerics. Everybody can do this. Everybody can use just use the best packages about solving differential equation, and you are happy. That's not true for partial differential equations. I don't mean that they are not packages. They are, but usually you have different integration methods depending on the kind of equation you have. So this is obviously not the only equation of partial differential equation. This is called the heat equation. It appears in thermodynamics, the heat equation or the diffusion equation, which is one kind of differential equation. But you have, for instance, wave equations, movement like waves. Okay, it's also partial differential equation, but it's called hyperbolic differential equations and so on. Need different numerical techniques for depending on the type of equation you have, of the type of the conditions at infinity or at the border. So there's no one package that you just plug in and you're done. So you have to know and a little bit more about numerical calculus and the basis of the theory of partial differential equations. And that's the reason that our projects that we want you to start working on the first day are non-spatial projects, non-spatial ecology things that do not require a partial differential formulation, because this would be really more difficult to implement. People would have to learn really numerical calculus, and there's no time in 1 week for that. So, okay. Now, this equation is linear. This is the heat equation. It's linear. There's no rho squared or logarithm of rho. There's no function. It's just rho on this side and the rho of this side. So this is the practical definition of linearity for us in this point. And so it's linear. And you know, linear, we know how to solve everything which is linear. Everything linear with constant coefficients. The coefficients are not variables and do not change in time and space. Everything linear is kind of indicates that, well, this should be easy mathematically, and we can actually solve this equation. And and here you have one solution. Okay, this is one solution. Again, solving, integrating, and partial differential equation is given the initial conditions and given the condition at the borders, what will be the solution at any time t bigger than 0. Okay, that's the problem, and that's usually can be done for this equation, but this is usually the difficult problem. So I'm here now saying, okay, I will have a more modest situation, and I will just show you one solution. And this is the solution, which is a Gaussian function. Okay, so how is this Gaussian? So first of all, it's a Gaussian because it's exponential of minus x squared. Okay, which is everybody has seen in the life. But then you have exponential of minus x squared divided by 4 times dt. And therefore, I mean, this is connected with the Gaussian, something like that. And this here is proportional to the square root of that. Okay? And the amplitude depends on time. You see the amplitude, the factor in front of the exponential, that's the amplitude, okay? There's some q, which comes from the initial condition, which is the total number of individuals. Then you get a function that depends on 1 over t to the square root of t. So the amplitude depends on that, and this over time decreases. Amplitude decreases, and the range expands. That's what a Gaussian is. In this case, a Gaussian, that's the solution of the heat equation, is something that goes down and opens, okay? Which is more or less what you expected from the laws. Yeah, you already saw that it will expand, but if it expands and the population is constant, then it has to decrease. And so therefore, there's a tendency of homogenization. The tendency is to be homogeneous. On the if the space is infinite, on the large time scale, the solution will be closer and closer to zero homogeneously. Okay, that's the large time for a Gaussian. And usually, you are not looking for that. You are looking for the transient and the dynamics, and so you see the widening of the Gaussian in time and the decrease of amplitude over time. Okay, so. And this corresponds to an initial condition. As I told you, that's a particular solution. It's not a general solution. In which you have at time 0, the population is concentrated on the point x equal to 0. So you have all the population introduced in one point, and then you look what happens over time. And what happens over time is given by this function, which is a Gaussian. So here's a plot. Okay, on time 0, you are concentrated at 0, and then you see you decrease and you expand. Okay, that's the way the diffusion equation gives you this result. Okay, so okay, this is just an illustration for two-dimensional case. Okay, two-dimensional case, but so you see, there's no big issue about 2 dimensions. It's just symmetric. So, however, we have, for the time being, just assumed that individuals are like molecules and they have a Brownian motion. Okay, but now you know populations reproduce, saturate, predate. There's all the population dynamics. So we want to cut this again into the game. So we want to have the population dynamics now, the real population. So okay, no, there's a comment before that. Okay, I'm skipping. This is an important comment. Now you could say I introduce a population here and it will spread. Question is, from a more biological point of view, would be like, well, what's the range of the population at a given moment of time? Okay, I introduce it today. In 5 years, where will the population be? Good question. Okay, nice question. Yeah. So, but you know, there's an awkward thing about the Gaussian. It's non-zero everywhere. And therefore, even if you give it concentrated at a point initially, in the next step of time, it spreads infinitely. So that's a problem with the Gaussian, okay? So we have to deal with this. So therefore, we will adapt our definition of range of the population by saying that the range is where I find most of my individuals, and let's say where I find 95% of our individuals, okay? That's a working definition, okay? You could also go for 99%. I mean, it's just the same thing, okay? So then you could also, so the problem is I have the Gaussian, I have the population, and I want to know, here, let's put here L, and here minus L on the X. What is the value of L such that I find 90%, 95% of the population inside? So that's clearly, if you have the solution, that's something that you can calculate, okay? So we want to do all the integrals because the Gaussian integral, blah, 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 but anyhow. What is important for us, so you would say the total population between, say, minus L and L is just the integral of rho, and the rho you know, it's a Gaussian, you can do the integral. But so, we'll give you error functions and so on, but the point is that the population is containing of a region which has this size. That will be the 95% of the population is contained in this region. Yeah. So, what is really nice is to see that, okay, this is proportional to the square root of time. Therefore, the speed of expansion is proportional to the time derivative of the square root of time, which is 1 over the square root of time. So this is the speed of invasion. And it is a decreasing function of time. Decreasing. Okay. If you didn't understand the math, don't matter. The final method, take-home methods, the heat equation solution on homogeneous space, if you define the range of the population where I find 95% of the individuals, then this expands in time, the region, and with a decreasing speed proportional to 1 over the square root of time. So, okay. So this was an important argument. Now we want to go back to what I was starting to discuss. We want to introduce movement plus population dynamics. Okay? Yeah. The expansion of a Gaussian is, implies infinite velocities. For many things, yes, because and this is one of the fundamental problems with using heat equations. So you can use other equations. Because the heat equation, okay, this is a little bit technical, okay? Heat equation had a kind of redistribution kernel of the population, which is non-zero everywhere. But you couldn't force a kernel that is 0 at a certain point, okay? So this would be a different kernel, and you end up with integral differential equations, okay? Which is a formalism which is used in spatial ecology. If you take a more advanced book on spatial ecology, you will find integral differential equations to take into account the kernel of redistribution. Here in this case, the kernel is just a Gaussian, which gives you infinite velocities. And because instantaneously you are at a given bounded region, and then poof, infinitely you get a non-zero solution. Well, the one way to deal with this is to give a new interpretation for rho, not as the actual density, but saying that it's the probability of finding individuals at a given point of space and time. And then saying that probabilities that are smaller than some value are actually biological zeros, and therefore you get something which is, it mathematically corresponds to say, I have here my Gaussian, it's infinite, but I actually will put a cutoff here, and then it's finite, okay? So, it's not very elegant solution, okay? But it's a solution, it's a practical solution to the problem, okay? So, okay, now I want to put the population dynamics, and I will do the simplest thing, considering that the population dynamics is completely decoupled from the movement dynamics, which might not be true all the time, okay? So that's a new, spatial ecology opens you up to a new set of problems which are much more complicated than just the population dynamics without space, okay? But, well, we do the simplest thing, okay? And the simplest thing is say, okay, the movement does not create new individuals or does not kill individuals. And the same thing is the population dynamics does not move people. Okay? So you have movement, and here the population dynamics. This would be Malthusian law, and this would be the logistic. So this equation here, it's a very celebrated equation called the Fisher-Kolmogorov equation. Fundamental, sorry. Fundamental equation of spatial population dynamics. It has been derived. Well, this is independent work. Fisher was working actually in population genetics, and Kolmogorov. If you are a mathematician, you have surely heard about Kolmogorov, which is one of the, one of the most famous scientists of the former Soviet Union, and one of the most famous mathematicians of all times, if you want. Okay, he had given contribution to many areas of mathematics. So this equation now isn't linear anymore. There's a rho square, so it's a nonlinear partial differential equations. We are in trouble. We don't have now a method of solutions. There's no analytical method to solve this equation. This equation cannot be solved analytically. There is just only one particular solution, but it's an actually non-generic particular solution. If you want to look for this on the internet, you have to Google Ablovitz-Zepetela solution. If you want to discuss after the class, I can give you the exact places where you find this. It's a particular solution. It's very simple, but it's not generic, meaning that a given initial condition will not approach this solution. Therefore, it's it would describe a situation where you have to have an exactly certain initial profile of the population, and only for that profile that you would have this equation. So it's kind of solution that looks like non-stable. It's not exactly non-stable, but it's not an attractor. Okay, attractor in this case has a different meaning. That our attractors, it's an attractor in a functional space, in the space of functions that are solutions to this equation. So you could think about an attractor there, but this is a problem of not anymore of qualitative theory of differential equations. It's a problem in functional analysis, which is beyond the scope of our school. So it's nonlinear, and it's called reaction diffusion because this is diffusion, and from chemistry, these terms are called reaction terms. Okay? So that come from chemistry, but so we will adopt the name, in ecology we adopt the name reaction diffusion, but we know, okay, there's no actual reaction and so on, but okay. Yeah? So, and the two-dimensional version is just putting the Laplacian here, okay? The same, the only modification is is in the spatial part. So, nice equation. Okay? So, no solution. Even nicer. At least you have some good mathematics to do on it, okay? Analysis of PDEs. It's still a research topic. You go to the Mathematical Institute of USP, there's a whole group working on partial differential equations, okay? So, but we won't go, and don't be afraid, we won't go for the analysis of everything. I will show you the results that you would obtain. You can say numerically, but you can actually prove that these results hold. And that's the work of Kolmogorov. Okay? And so if you start with a population which is released at a certain point, and you suppose that Fisher-Kolmogorov equation is the one that explains your population dynamics and your movement dynamics, everything, then, which is not anymore the simple diffusion equation, which didn't have these other terms. Now you add these terms, You don't have explicit solution, but okay, look what happens. Expansion and increase of the population. Why increase? Well, because there's the dynamics of the vital dynamics, and there the population increases naturally because it's a logistic part. Logistic will increase, but then it will also saturate. So this is just doing I mean, the outcome here is just what you expect from the input. The input says you have diffusion, you have growth, and you have saturation. Here you have diffusion, here you have and growth, and here you see saturation, okay? And continuous expansion. Therefore, what will happen is it grows up to a certain saturation and then expands. Yeah, tell me. U is rho. Ah, okay. I just copied this from some other book, and the book doesn't use rho, but it's U. Okay, so yeah, so this is U is rho. Okay, so this is the population density over time. So it expands, it saturates. So that corresponds to the idea of a real biological invasion. You have a population that is introduced and it will establish there. Therefore, it will grow and saturate, but it will also expand its range. Okay, so it's better from a biological point of view. It still has the same problems of infinite velocities and so on, but we don't care about that. And the point here is this solution, it has a kind of front, and the speed of this front can be shown to be 2 times square root of a times d, which happens to be a constant. Okay? It's a constant. So the speed of invasion is a constant. When we use the Gaussian, the heat equation, without the terms of the vital dynamics, of the population dynamics, we had obtained that the population range expands with decreasing velocity. Here we obtain different result. The speed of invasion is given by a front where the front expands with constant velocity. Okay? So.
Without the reaction part, so the example before, the maximum part of the curve attains 1 only at the beginning.
Yeah.
And then it decreases.
It decreases. Now it increases because you have the creation of new individuals.
And with this one, it hits 1 and there's some
Yeah.
part of
It gets saturation here. You see, 1. I wrote 1, but this would be actually proportional to A and P. Okay, this is a non-dimensional case. Okay, so it gets to 1, which is a solution to the part of the equation of the vital part. So 1 is a solution. If you put, think A and B are 1. Okay, it's just for easy calculation. So if you have 1 here, then 1 is a solution to this part, and it's almost a line. Therefore, the second derivative is 0, okay, and therefore the population should not change anymore and get to a static profile in the center. Yeah. Hmm? Of progression, yeah, with time. Yes. Yeah, then it would be like this, because here you have increase of population. You see, that's just a Malthusian term and a saturation term. Okay, so that's the logistic. Therefore, the population actually increases. Okay, So the idea that you have a constant population, a decreasing population, comes from the fact that you expand, but if your population is constant, it has to decrease, because how could it expand without decreasing in the case of the heat equation? Now, it will expand, but there's a process of birth and death such that the population actually increases over time, okay? No, the constant speed is the speed of the front. There are many ways of defining this. You can define this in practical terms. Sometimes you just make a cutoff, and you see here the speed of this part of the solution. And you can also show that there's a front, and the front moves. I mean, it's more mathematically difficult problem to show that, okay? But it's possible. And yeah, so you have expansion, saturation, and growth, saturation, and expansion. But the difference with the heat equation is that the expansion now is with a constant speed. So here another mathematical comment that is, I say this is a solution, but it's a particular solution. And you would say, come on, now I give you an initial condition, which is, say, bounded in a certain region. Why should I believe that this solution will be like an attractor, that after some time, my actual solution will look like that? So, thanks to Kolmogorov, he showed that every bounded initial, bounded in space, so that's every solution that is that's zero, initially zero, outside of a certain region, every solution for infinite time will approach a front with speed given by this, right? So it's general, right? Okay, you could also say now, well, maybe that's a particular case because it has to be a solution technically on a compact domain initially. What happens if I have an initial infinite distribution, and then everything depends on the rate of decay at infinity, and more complicated things happen, okay? So, but for practical uses, every study of invasion, there's initially introduced at some point, and there's no population at the other, so this is okay. Yeah? So, we may not be able to look for data on the precise form of the solution, but we have found two different patterns of invasion, one with decreasing speed and one with increasing speed. So when do you expect to see one or the other? So if the time scale of the movement dynamic, of the expansion dynamics, given which has to do with the d, is the same time scale given by the growth parameter 1 over a. If you're on the same scale, then you expect these things to happen. If you are in a scale where the spatial part changes much more quickly than the population dynamics, then it's like a good approximation to just get away with the population dynamics, okay? But if you do this, you are not really seeing the invasion process. You are just seeing the movement, okay? So that's a discussion that all these terms here should be of the same order of magnitude in order to be relevant for an actual problem, okay? And that's why sometimes the the spatial dynamics on, say, every day on a scale of 1 hour, okay, is not relevant to the actual invasion dynamics, because invasion dynamics has to do with the increase of the population, and population increases, say, over years. Therefore, you have to take care with this kind of thing, okay? So you should be having here the same time scales of all these three terms here. So, we actually obtained a solution which has a lot of characteristics, but we obtained the speed, and the speed does not depend on the parameter which is in front of the square term, it's only of the b. So the speed does not depend on b, okay? Which means that I could, for this case, I could study maybe only the equation without the b. It's called the Scalum equation. Scalum is very important, ecologist and mathematician. And so this is will have unbounded solutions, okay, because there's no saturation. But from the point of view of the wavefront, it is okay to study this equation. And this is linear. Ah, okay, linear we like, okay. So, what about data about this? So Scalum was the proponent of this and so on, and he went for data, okay, historical data, not experiments. And so welcome to the classic example of the muskrat, which is a rodent native of North America. It was introduced in Europe, and it was a very precious thing. People went to hunt muskrats in North America and bring them to Europe for consumption, mainly for the fur. Yeah, yeah. They didn't eat them. I think. I mean, it's used for the for coats. Yeah. Okay. For coats. Yeah. Yeah. And also for perfumes, I think. Some perfumes. Yeah. Yeah, they use you use the part of them for perfumes, okay. People don't want to know this because you get perfume and you don't think, oh, I have a rat here, okay. I think so, yeah. You know, the old kind of men perfumes, you would call it musk, come from muscat. Another animal? Okay, so. Ah, okay, so. Okay, okay, okay. Okay, something that's not done anymore because people don't use anymore this kind of coat because of animal coat, okay? But anyhow, back at the beginning of the 20th century, it was very, I mean, praised in Europe. Very, I mean, it's very elegant thing. So, but some people in Bohemia at the time, in Prague, just decided that why, instead of hunting then in North America and bringing the material back to Europe, why don't we just import them alive and we make a creation and we grow them and then we have everything here. We don't need hunting, we don't need transportation. So it's just such a nice thing. So what happened? They did this, but somehow, I don't know the story, they went bankrupt and it didn't work. But so they just released the muscat in the nature, okay, bye-bye. So this happens nowadays also. There's a famous invasion of a kind of crab. I can't remember now exactly the name, which is aquatic, and in Italy. I can't remember the name now, okay? But it, crayfish. Crayfish is a thing that you eat, and it's natural. It's from the region of Louisiana, New Orleans, and so on. Crayfish, yeah, you get this fine fish there, and it's not a problem. It lives there, okay. So people that took this to Italy and had a crayfish, a crayfish creation there, and something happened, and then they just released the crayfish, and they invaded all rivers of, at least of northern Italy, because they had no natural enemy there, and so on. It was a problem. Okay, so this kind of biological invasions by this kind of situation is an actual thing that happens. So today you have millions and over Europe, but actually we can the expansion where the muskrat was found was followed by 17 years around Prague. Okay, so nice. We have an actual experiment. We release 5 individuals at a certain point, and it will expand. So we should expect Fisher-Kolmogorov equation to be okay. But Fisher-Kolmogorov is homogeneous space. But well, this animal didn't care much about the rivers because it can cross the rivers. Okay, and it just went on. I mean, it just found Europe marvelous. So it's an expansion for this muskrat. It's like homogeneous space. There are no barriers. Yeah? So you will see here, that's 1905, and then you have 1909. So that's the region. Here inside this, this region, you have the muskrat. So then 13 here, and 17 here. I think there's one more, and 21. So expanding. Okay, then you'd say, yeah. Well, first of all, it's two-dimensional. It's not symmetric in X and Y, okay? But more or less symmetric, okay? You could, well, imagine that, well, I have a form. You have a form like that, okay? You could fit a circle, okay? Some circle that had more or less the same area. Okay, you can fit a circle, and yeah. So consider this to be a circle. Okay, it's not like people like to make the joke that consider a spherical cow. It's the name of a book, but consider that this is a circle. Okay, and a circle has only one parameter, which is the radius. Okay, so this expansion here can be seen and approximately as expansion of a circle with a given radius. Therefore, the radius will be variable in time, and it's the expansion speed of the radius is the expansion speed of the range where you find the muskrat. So you could ask, okay, heat equation says that this speed should decrease in time. Fisher-Kolmogorov and Scalam say it should be constant in time. And okay, you get this. It's the radius here. It's the time here. That's the radius. And it fits exactly a line. Therefore, the inclination is constant. Therefore, the speed is constant. Okay? And that's, I mean, it looks like it's too good to be true, actually. Yeah, you don't even, yeah, but it's really, really nice, okay? You don't even have to know, you know, there's a method of fitting things. It's just making the plots larger, and then everything seems okay. So even without this trick, it fits quite well, okay? So, rejoice, Scalam has a point here, real point. Expansion width, constant speed is explained by the Fisher-Kolmogorov equation, okay? With all the simplifications. That's really nice. We have done much more simplifications than when you studied only the population dynamics with ordinary differential equation. Here we had to make lots of assumptions. like Brownian movement of individuals, and lots of things, Fick law, and so on, and blah, 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 okay? Wow, but it works. It works. So really, really a good point. Will it work always? Well, obviously not, okay? Because all the simple assumptions can be modified, and you have the whole area of spatial ecology to study where you will see deviations from this kind of thing, okay? There's a recent book called The Mathematics of Biological Invasions by Mark Lewis and Petrovsky, which was a lecturer here, actually. And Mark Lewis also visited us, so friends, and therefore it's good. Which is about all of, this is just the first part, I mean, the first chapter is the diffusion equation. Then they go for more integral equations and so on and so on. So it's very nice to study. If you are mathematically minded, it's also very nice because there are real mathematical problems behind, okay? So, okay. Now, for the theory of Brownian motions, you can see as the mean square displacement per unit time, the d, okay? Because, so when you went back here, we just wanted to explain that the speed is constant. Could we predict the speed? Through Fisher-Kolmogorov equation, the prediction depends on the diffusion constant, okay? Which is natural. If the constant is big, then obviously means a lot of movement and a higher speed. And if the constant is small, means that the spatial part is varying slowly, therefore the expansion speed is not so high, okay? But until now, this was just a phenomenological constant, okay? But could we find a mechanistic way of calculating this phenomenological constant, looking at the individual movement and scaling up to population size and then getting effectively something which is the calculation of the diffusion constant, which is really nice, okay? So, yes, you can do this. It's a topic in stochastic dynamics, okay? And people do this. You did this on the last course, yeah? Yeah. There was a 2 months course on stochastic problems in population dynamics. Not only in population dynamics, yeah. The course of general stochastic to ecology. Yeah, okay, because it's Ricardo Martinez, which is the organizer of the second week that gives this course. So it's a problem that you can study and so on. So, very nice, but then you could, okay, just take the results of this, all of this, and then you'd say, this is actually, can be calculated. So we could think about tracking individuals and calculate it. But here you have to be very, very, very cautious. If you do this, it's likely to get a wrong value for D, usually too large. So, why? So if you want actually to describe the ecological problem of the range where you find a certain species, you are not looking at the daily movement of the species. Let's say it's an animal. It's not a daily movement. So, for instance, if you take some rats, you want to see the dynamics of the spatial distribution of the rats, like the muskrats, okay? It does not depend on what the rat is doing every day. It depends on what? On the establishment of new homes for the rats, because they have home ranges. So the rat is actually, say, going on here and here. At the end of the day, he goes back to always to the same point. Therefore, there is no range expansion. What expands the range is the creation of new new homes for the rat. Or if you look for ants, like the Argentinian ant in California and so on, it's the creation of new colonies. It's not the daily movement. They are going here just in a line. And that's not important, but at the end of the day, they go back to home. And if go back home, okay. It's the range where you find the species is not connected to the daily movement. That's the wrong time scale. The range for certain species which have homes, and they have therefore home ranges, is where you find the species determined by where you find the homes, which is a process that has a different time scale, which is different from the everyday movement, and will be such that the expansion of the creation of new colonies and so on will be on the same time scale as the population dynamics growth process. Okay? And then you have like the muskrat. So Scanlon only had the ranges, so we are at the population level all the time. So it didn't try to follow the rat. Okay? But a friend of mine actually followed one rat. One not, many rats. So there's a problem of a disease which is common in the arid parts of United States and also in Argentina, which is the problem of this hantavirus. And that there's new species of hantavirus was discovered, being up to, which makes you really, gives you a respiratory syndrome, and it's 60% of the cases, human cases, it is, you die. Okay, so you better don't want to have contact with this disease, okay? And it is transmitted by this rat. Where you find the rat, you find hantavirus. Therefore, the expansion of the disease is connected to the expansion of the rat. And not only the expansion, but there is also an epidemiological thing going on here, okay? But so you would expect that the spatial dynamics of rats has something to do with the spatial dynamics of hantavirus, okay? So this friend of mine, it's a retired professor, Nitan Kenkre, from he's original from India. Very, very nice person, because he's originally from India, but it's from Goa, and so he understands Portuguese because Goa was a Portuguese colony. And but he immigrated to the United States, and he was a professor in the University of New Mexico in Albuquerque, and actually had an interdisciplinary center for exchange with South America, with Latin America, things, and so people went there. I was there, my students were there. Okay, now, well, he retired because, he's an older guy. So he got interested in this problem. He was an atomic physicist, actually, but he kind of switched it like me. Also, I did atomic physics at a certain point. So, and he was like, okay, what a mess! I cannot know. Gee, this is phenomenological. I want the real thing. And he convinced people from the biology department to make experiments with the rat. Okay, I don't know the details of the experiments, but they would be tracking the rat during a certain amount of time. And so they calculated D, and got the result like the range. Using this calculated D, the prediction is that the invasion would take all of the United States in 1 year, something like super high velocity invasion, which is not observed. Okay. So what was wrong? The wrong was actually that there are home ranges and there are homes for the rat, and you have to take into account the process of creation of new homes through immigration of juveniles forming new home. Okay, and well, then if you have data on this, and actually they had data, then you could model all the process. It's much more involved, but they have a very nice model for this. It's done by Nitan Kenkre and another friend of mine from Argentina, I think, yeah, Guillermo Abramson from Bariloche. And that's an epidemiological dynamics, instead of having with vital dynamics, epidemiological dynamics, and spatial dynamics, but of the expansion of the homes, and actually this can be fitted very nicely. It's very good work. It can be fitted to data, and everything is nice. And okay, you can now, okay, you can be, okay, they have got it, okay? So it's a very interesting lesson about mechanistic calculations that you better recall what I told you in the, I'm running out of time. Ooh, come. This is not working, so time stopped for me. Okay. So I'm okay, I'm finishing. So this is a very a nice lesson about mechanistic, the relation of mechanistic calculation and phenomenological models. And in the first lecture, I told you at the end of the first lecture, pay attention, models are valid on certain spatial and temporal scales. And here you have a problem of scales. You have to be on the right scale if you want to describe a biological phenomena, like the expansion of the home ranges of certain species. You have to be on the right time scale and the right spatial scale. Does it mean that you should not study the everyday movement of this rat? Sure, you can study this. It's movement ecology, whole new branch of science. Okay, how is the behavior of a species, the movement of the species? How is the distribution of steps of the animal? Why does the animal move? It's going for foraging, just getting nutrients or whatever. It is a predator and they just run away from the predator. So that all of this is done on a scale which is not the scale of the population increase. Therefore, you don't have to put the vital dynamics in many of these cases. Sometimes you will study this only on a shorter time scale where the population is effectively constant. Therefore, you forget about the vital dynamics, but then you want to study the details of the movement dynamics beyond the approximation of Brownian motion. Okay? This takes you to nice things like people like to mention, and a lot of physicists like to work on that. There's actually a good group based in Curitiba with Marcos Eleutério da Luz that studies movement, and then you get one of the basic elements of your study will be, say, if your movement is like that, okay, which is typically a foraging movement. You move around and then you stop a little bit and then move. Okay. So you have a distribution of the size of the movement, okay, which is connected to your foraging strategy, okay. Then you can put the size here and look for the distribution here, okay? And well, there are a lot of people that look here and they see that the decay is not exponential, it's polynomial, and therefore that's a long tail, okay? Distribution, which is kind of, has been the hype in physics for in the 90s and the beginning of the century. And so people are really, physicists get hot with that. Yeah, long-tailed Levy flights. It's called Levy flight. So what's a Levy flight? It's a movement like that. There are some very large steps, rare. So you have two scales. The scale here of these movements and large but rare steps, which correspond to this part. This is large steps, It's not decaying exponentially. It's decaying polynomially in such a way that you can still observe some events of large steps. So now I have a story about that. That's very interesting from the perspective of how science works. Okay, that's a fine story. So a bunch of physicists around one very famous guy from New York, which I can't now remember the name, Stanley, which is a person which is very important in statistical mechanics. I think he's a recipient of medals and so on. Seems like pretty important, okay? So, together with a bunch of Brazilian physicists, Marcos Eleutério da Luz and Gandhi from he's now, I don't know, I think in Natal, okay? And other people, the Raposo, they went for data, and they had data about the movement of albatrosses. Albatrosses, okay? Some ecologists in the past have put some sensor in albatrosses and followed the movement. But this was before the age of GPS and so on. It was a sensor that was sensitive to water. So what you have, it's the albatross flying, and then it goes and gets a fish. Then it, poof, gets the fish. Then you get a mark on your sensor. Okay, and the sensor obviously it tracks the time. Okay, so you know, the guy flew 20 minutes and he got a fish. Then he emerged, and 5 hours later, again a new point. So what you get is now the hypothesis that they made is that, well, that's the time between X of fishing, of consumption. The time is proportional to the distance, because, well, it more or less flies with constant velocity and so on, good approximation. So the time obtained should be proportional to the distance, and they obtained that the foraging behavior of albatrosses followed a Levy flight distribution, published in Nature. This created a whole bunch of people going around looking for foraging behavior and Levy flights. People went for, I don't know, years in Russia. And well, lots of things have found them. Sometimes have Levy flights, sometimes you don't have Levy flights. Oh, come, that's so nice, and so on. Okay, and then the ecologists that actually got the data heard about that some years later. Okay, I think the guy had, I don't know, he got off of universities. I don't know what happened to him. Anyhow, but it took a time for him to know that his data had been used. But he still had the original data. Okay? And he knew something about albatrosses, because Stanley and Marcos and Gandhi didn't know anything about albatrosses. They're just flying objects for them. So they fly and fish. Oh, that's what albatross is for them. And then he knew something about the albatrosses, and he said, no, I never see this kind of behavior. I don't think they going on fishing here, and then they go fishing somewhere kilometers away. I never saw this. How come are they saying that this is happening and based on my data? And then he went on to discuss this with Stanley and the people, and did you notice that the Levy flights occurred in a certain time of the day? And the albatross was not flying. He was taking a rest. Oh. Albatrosses takes rest, goes on an island and stays some hours there without. So the hypothesis was that they were foraging all the time. So no, but they don't forage all the time. They actually also take some rest and stay in some place. Okay? So they are not flying with constant velocity. It's completely wrong. So if you look for events at a certain period of the day, I don't remember which one, and you eliminate them and say, okay, this is a guy taking a rest, you get a Gaussian distribution. No, I mean, and you get exponential decay. Okay, they're not Gaussian. No. Exponential decay. Okay, so what happened next? People took this seriously. Stanley and these Brazilian colleagues actually took this and made a study and actually could show that using more advanced statistical techniques like a criterion to compare different explanations for the same data and so on, that they actually prefer the best explanation is I think, exponential decay. So, because they didn't even try to fit an exponential decay with the first data, okay? They just went, oh, it's polynomial, okay? So they went on, and then they actually published, 10 years later, a new paper with the correct interpretation and the correct saying that, sorry, we are wrong. And they published this in Nature again. Or Science, I don't know. So it's the way to make, yeah, well, famous people have an easier life. Yeah, I mean, none of us would be able to get 2 papers in Nature, one, and 10 years later saying, oh, I was wrong, sorry. Okay? But Stanley could, actually. Yeah, and yeah, okay. So and then this actually motivated, I mean, not a loss of interest in the area. People doing movement ecology all the time, okay? But the physicists going on and fitting polynomial decay for everything and saying that's a complex system, that's a different foraging, and there should be connected to criticality in statistical mechanics, and it's a whole fantasy, okay? It's a whole... Okay, so that's it for today. It was longer than I predicted, actually, prepared. So here you have, now you have different bibliography. You have, as well, Murray, Britton are the main books we use for this course. But there are these other books which are very nice. The one of Cantrell Cosner, You Better Be a Mathematician, or a physicist with mathematical mind. It's a spatial ecology via reaction diffusion equation, but it's like theorems, lemma, corollary, and so on. And Okuba and Levin is more like the things I have done. Showed here, diffusion and ecological problems. And then there is the quantitative analysis of movement. It's a book which relates data to actual models and data and so on. And then there is this book of these friends of mine that Levin, Petrovsky, and somebody else, I can't remember the name, and I think a person from England, which is the mathematics behind biological invasion. Yeah, you raised your hand. Yeah.
I want to know if you work with sessile organisms.
With sessile.
Work on these kind of problems. You can have plants that have reproductive rates and
Yeah, yeah. So I don't know. I'm not specialist on this sessile things. But I mean, there's a lot of studies, and I'm very world-renowned specialist on plants which expand through an animal. Okay, how is this called? Yeah, you have the tree, and then you have the fruits, and then an animal goes there and takes the fruits or eats the fruits, goes somewhere else, and then you have a new tree here, because the animal took the thing. Mauro Galetti from IUNESP is a very famous specialist on this kind of thing. So, but he is not a mathematically minded person. So there are a lot of data about that. I suppose that there should be work on the mathematical part. I suppose so. But I'm not sure, but I cannot cite one at this point. Okay, I have not seen this. You have seen something? Or? I mean, I suppose that it's doable, and I think it's a typical thing that people would have asked themselves to study. Okay, because yeah, plants have a nice thing that you can track them easily. Yeah, over a long time, over a long time, you can track there because they don't go away, okay? So for instance, for trees, you have census of trees being done in parcels and so on, very nice, okay? So any other question? Yeah. So, yeah, you. Pierre? Legend. Yeah? Yeah, actually, I don't know. He has a book on that. I don't have. You know this, Paulo? It's not a modeling approach. Mm. Okay. Yeah, yeah. Yeah, it's about. So, any other question? Yeah, you. Paulo is a specialist on imperfect detection, yeah? You. I mean, statistical models in this case, yeah? Okay? So thank you. Good work, hard work, come with results. Today is day of results, okay? You be really, really focused. You get the results, okay? Yeah, D-Day. Thank you.